This physics example problem deals with a clock regulated by a pendulum, where this clock is on Earth at first and then taken to the moon for some odd reason. So this simple pendulum clock is well regulated on the Earth, keeps accurate time. The length of the pendulum is unknown for us, don't know what it is. So we have the astronaut taking the clock to the surface of the moon, or some moon tourist in the future as I record this video. Will the clock run slow, or will it run fast while it's on the moon, or will it keep good time? Let's assume it's going to be an error. What will the error be after 24 hours actually elapse? What will the clock read for the elapsed time? So if we take a look at this, for a pendulum that's swinging back and forth, that's regulating the time, the period of oscillation of the pendulum depends on the length of the pendulum divided by the local acceleration due to gravity. And that's where the difference comes in. We're going to take the same clock, so L will be a constant, but the value of acceleration due to the gravity on the moon, roughly 1.62 meters per second squared compared to 9.8 on the Earth. As this pendulum swings back and forth, doing the tick-tock type action, for each swing, it allows a gear to move, and that gear then moves other gears, that moves the analog hands of the clock. So that's why the pendulum swing is important. So what do you think is going to be true about the period of the swing on the moon compared to on the Earth? We're dividing by now a smaller number, 1.62 instead of 9.8. So this time is going to be significantly longer. The time for the pendulum to complete one oscillation, it's going to be significantly longer until the pendulum gets back to release the gear again so that the hands of the clock can move forward. The clock is going to run slow. It's because the gears are not going to be activated as often. The period of the swing is larger on the moon than is on the Earth. On the Earth, there's more restoring force. The acceleration due to gravity is stronger, so it pulls the pendulum back down vertical more rapidly than occurs on the moon. So let's divide the two equations for period, one on the Earth and one on the moon. Excuse me. When we have, we're having two equalities here. Time on the Earth is equal to square root of L over 9.8. And separately, there's an equation, time on the moon is equal to square root of L over 1.62. So we can divide those two equations. That's a legal activity in algebra and math, as long as we're not dividing by zero. The L's cancel. The length of the pendulum is the same. It's the same clock on both the Earth and the moon. So we get to the square root of 1 over 9.8 all over 1 over 1.62, invert and multiply the denominator, and we find 1.62 divided by 9.8. Pause and look at this if you need to. Verify it by putting in numbers into your calculator. But we can find the ratio of the times by the square root of 1.62 over 9.8. You should do that on your calculator, and you should come up with fairly close to what I have here, 0.40658, the ratio. Excuse me, the time on Earth, the period on Earth is smaller by a factor of 0.406. Another way to say it, the oscillation time on Earth is about 40% of the oscillation time on the moon. So we can multiply 24 hours by this ratio and find out how much the clock on the moon advances during 24 hours. It's only going to advance 9.76 hours. So our time difference, our clock is in error by 14.2 hours, roughly, for an actual 24 hours of elapsed time. So ask your instructor if you have questions on this. If you want to see other physics and astronomy videos, please go to this free website. If you like the videos, please subscribe to my YouTube channel.